Give me 1 sec. Man, there's a lot of stuff.
Can you reach your hand out?
Like that?
Yeah, I just want to see the limit. Where is it at? Okay, so it was, I didn't want it to pick up your pencil.
All right, which problem?
It's the very last one, finding directivity as a function of the normalized
Okay.
power.
Yeah, give me one of the values.
Normalized power is sine squared theta and cosine squared phi.
Cosine squared.
Yes, sir.
Phi.
Yes, sir.
And so this is a mathematical function. It's given. This is really, you're not going to be exposed to this in the real world. You're going to measure patterns and get directivity from it. That's really the way it's done. However, in order to get familiar with this, we take that as the normalized power density. It's already normalized, which is nice. It's in spherical coordinates, which is nice. And now we find D max, the maximum directivity. That's equal to 4 pi over, and this is that double interval that I'm going to talk about in a second. Let's see if I get a darker marker. I need to throw those out. And that one. Is there a wastebasket?
I don't know if there's a wastebasket. There's a lot of markers over there.
Those, yeah, I'm going to try those. We're going to do something. This is becoming a wastebasket. And I'll grab those before the quiz. This is the double integral of the normalized power density, right? Let me just put it up first. It's P normal, right? And it's times sine of theta d phi. Theta goes from 0 to pi, and phi goes from 0 to 2 pi, technically. That's the way so that's the definition of D max. And you have to know this. You all with me? Now, for our particular problem, we find out that the maximum directivity is equal to 4 pi. Then it's the integral from 0 to 2 pi. The integral from 0 to pi. Here's the normalized power. And it's sine squared of theta, cosine squared of phi, and then it's times the sine of theta, d phi. I'm going to make mention of something here. This one's also running out. Which is nothing. That one is. I'm just going to throw them off. I'll get those in. I'm trying to get rid of those bad ones. Purple does. Suspect. I'm gonna get some. That one may be a late bloomer. It may come to life. I'm gonna just try this. So when we do this in Dr. Moore's book, I'm just gonna say this. Normally he puts D max as equal to 4 pi, and this will be called omega sub p. Omega sub p is termed the solid angle. You don't have to worry about that. It's this is in stair radians. You know, in the circle of measurements are done over one dimension for any kind of an angular measurement. They're degrees, right, or radians. If they're measured over a solid angle, in other words, over 2 dimensions, they become stair radians. And there's 4 pi stair radians in a sphere. If you think about it, if you just integrated over a spherical surface from 0 to 2 pi, 0 to pi, you're going to get 4 pi square radians when you do this. And something else I should say too, that D max is also, I don't spend a lot of time talking about that right here because it's more for antennas. When we get further along, if you were in, take a 400 level course in antennas, we talk about that a lot more. This is 4 pi, and then what they'll have is the integral of d omega over the entire spherical surface. but that d omega is just sine theta d phi. So in essence, you don't need that. You just need this. You just need this, I should say. You with me, class? That's the reason I don't spend any time on that. It doesn't add to the understanding of the application, how to do this. So when we do this integral here, I'm just going to tell you right now, take one look at this. I got a sine squared, another sine, that's a sine cubed. Do you agree, class? Here I got a cosine phi times phi, right? So what I'm going to do is just focus on that integral. I'll even call it omega sub t, from 0 to 2 pi, from 0 to pi. Now I got sine times sine is really going to be what? 1 minus cosine squared theta times sine theta d theta. And then I have the cosine cube, or cosine squared theta d theta, right? With me? Now y'all remember, this really we do by substitution, don't we, class? And when we're all said and done with this integration right here over theta will result in simply 4/3. Do y'all remember that? So what I'm going to do is say this. I'm not going to do that one again. I can't if you want me to. I got the integral from 0 to 2 pi. And then this integral right here, when we do it from here to here, that's going to result in 4/3. Okay? I'm just leaving it there because we know that. Now I have cosine squared theta d theta. Well, how do you want to do that? Cosine squared, you can use Euler's on that. And you can do it with individual Eulers. Or you can use the half angle formula. Do y'all remember that? Half angle formula? No. You don't have to know it. But what do you know for half angles? Or better yet, why don't we just do it this way? I'll show you. And this is not that important, so I'm not going to spend a lot of time on it. I know cosine of phi is e to the j phi plus e to the minus j phi, right? Or phi, pardon me, over 2. Isn't it, class? You agree with that? That's Euler's identity. So if I square it, I like showing it this way. If I just take this and square it, then what do you see happening? Well, if I take cosine of phi squared, that's that squared. You agree? Now, follow me. That's going to be what? I don't know if Dr. Tudnate shows you that, but 1/2 becomes 1/4. Agree? Now do the terms. I have this times itself. That's e to the j 2 phi, right? That's the first one. The last one is e to the minus j phi times e to the minus j phi. That's e to the minus j 2 phi. Do you agree with that? Right? Now what about the cross terms? This times this is 1, isn't it? And that happens twice, so you get 2. Do you agree with this, class? Everybody follow me? I'm doing it this way because these, if you ever get in trouble, oh, I don't remember that half angle or that cube angle or whatever the trig identity you want to, you turn the trig function into its Euler parts and just do the math. Squared, cubed, whatever, and you'll always be able to group them. You don't even have to do anything more than integrate this from this point on in there, but I'm going to show you the trick. So then cosine squared of phi equals, now follow me, I have 1/4, right? And then I have 2 plus this business, e to the j 2 phi plus e to the minus j 2 phi, right? And that's it. Now I'm going to take this 1/4 through here. You probably see this, right? I get what? 1/2 here, right? And this is divided by 4, right? Now take a good look at this and this. What if I make this 2, right? And then I divide by 1/2. You see how that's that? How many see that? And In the back, far back, you guys see? So I just replaced this with cosine of 2 phi, okay? And now I think you know the answer to this now. So now I go ahead and I put this as 1/2 plus 1/2 cosine of 2 phi d phi, right? And what's that going to be? I'm going to do the first part. Look, I should do it like this. That's the d phi integration. It goes. So if I have 1/2 times 4/3, that's going to be 2/3, right? Integrate that from 0 to 2 pi. It will be 2/3 times 2 pi. I'm going to leave it as that. That's the first one right here. That's this. D phi is just phi evaluated from 0 to 2 pi is 2 pi times 1/2 times 4/3 is this. Now the second part is what? The coefficient becomes 2/3, right? Now what about this integral? Cosine of 2 theta, or 2 phi d phi, how do you do it? What do? We do a u substitution, don't we, class? We just say what? If we want this integration, when we integrate cosine of 2 phi d phi from 0 to 2 pi, right? We just let u equal to 2 phi and du equal to 2 d phi, or this becomes the integral cosine u, right? And then d phi is really going to be du over 2, right? And then the limits, since u is 2 phi, this is still 0, and the upper limit becomes 4 pi, doesn't it? Y'all follow me what I'm doing here? Right? And what is that going to be? Well, that's 1/2, right? And then cosine of u integrated is what? Well, you know what? The derivative of cosine is minus sine. The integral of cosine is sine, isn't it, class? So then it's going to be sine of u, right? Evaluated from 0 to 4 pi. All right. What do you know about the sine of 0? It is? 0. What about the sine of pi? What is the sine of pi? 0. Sine of 2 pi? 0. Sine of 4 pi? 0. It goes away. In other words, that goes away. And that means that this right here, which is 4 pi over 3, is what goes downstairs. So then this is going to be 4 pi over 4 pi over 3, or simply 3 is the max. Do y'all follow me? Now please listen to the next part. This is important. That integration I don't worry about. Most of your calculators do symbolic integrals, and in the real world these days, it's rare for somebody to really angst over integrations. If they're not completely obvious, they'll put it in some tool that does symbolic integration. I'm just telling you this, and one of the tools, you remember this now, that you'll like is Mathematica. If you ever get a complicated integral differential equation and you want a closed form solution that you can cut and paste into an article, Mathematica does it. Remember what I'm telling you. It's Mathematica. It is literally ready to go. It'll put it in a LaTeX form. I think you can even get it into like a math type form, like Word documents, but it's fantastic. Okay, so that's 3, but that doesn't quite answer the question of the directivity for all angles. The actual function for directivity will be d max times the normalized power density, which is the function of theta and phi. So what you do is you take this d max, which is 3 that you calculated, and then you multiply by that normalized power density, which is this business. Okay, class? And that's how you get the directivity in general for all angles. Y'all with me? Another question? Thank you for that. That's a good question. Anybody do that one with angst? If you did it and you were wondering, huh? Well, don't worry, it's just integration. That's all it is. Any other questions? Really? Nothing? Yeah?
Are you going to remind me about that voting?
Oh yeah. Sorry. Class, the way how many have had me before? Couple. I let you select the day of your test. I don't do it. I mean, if you want me to, I will, but you're foolish to do so. Y'all have things on your plate. So what I would like to do is this Monday, not now, but on Monday, vote on the day of your first test. Now, no matter what is voted on, usually at least one person has a problem with that day. But it's the best I can do. And if you know a better way, let me know. Say, on Monday, we're gonna vote on the day of our first test, all right? I'm gonna make one suggestion to you. Don't do it the Monday after a football weekend for only one reason. He's in the class. And he's the long snapper for Auburn. I'm kidding. Now, if you want it, then that's fine. But I'm just saying that you select it, doesn't matter to me. Please talk amongst yourself about when other things are due. Look at your schedules. And don't vote on a date without knowing what your calendar has in front of you. Because I've had this happen where kids have voted on a date and then they come piling into my office and say, but we have another test that same day. Once it's set, it's set. So please, Monday, fair enough on that one? Please remind me, everybody, okay? Now, questions regarding the homeworks and stuff. Because I gave you a bunch of little Hertzian dipoles. I gave you normalized gain. And by the way, yeah?
Can you write number 1 from homework 12?
You're gonna have to tell me what it is, but absolutely. Let me just say one other thing too, before I leave this. I gave, the normalized power density for this one was given, right? Please listen to me on this one. I'm gonna get to you in 1 second. Suppose this was what was given. And what I'm saying here may be of real benefit today. Now, I can't be any clearer. So listen. Suppose I gave you an E field. It was like 20 e to the minus j 30 pi r. And then it was times, say, I don't know, the sine of 20 phi, or 20 theta, which is a bizarre kind of thing, over r, a phi, and I wanted to know d max. Y'all follow me? I give you an E field, and I want to know d max. How do you do it, anyone? Well, what does d max require? 4 pi over that integral of what? Normalized power density, sine theta d phi, right? This is often termed d omega, but you don't need to know. Do you all agree with that? Everybody hear me now? So I need this, right? That's normalized power. How do I get the normalized power density if I give you this for the E field? Anyone? Think, how would I get the power density? Let's go there. How would I get the power? I got the E field. Dr. Baginski asked me how I get the power density. Anybody? Go ahead.
So 1/2 e squared over.
He's thinking, yes. So if I wanted the power density from this, then I would say is P average, this is the average power density, would be 1/2 magnitude of E squared over eta, right? Y'all see there would be a sine squared in there, right? Sine squared is something that's not just phi, it's 20 phi, but sine squared nevertheless. Do you all agree with that? Now once you have that, we're still not there. We need the normalized power density. What would you do without doing all the math? I take this, I square it, I get something over r squared, right? How do I get the normalized power density? It's really easy. This is going to be a sine squared, right? We know the normalized power density will only be a function of angle, right? Will not be a function of r, correct? So what do?
Divide by the sine squared.
I divide by everything in front of the sine squared, and I'm left with just the sine squared. That's my point. My normalized power density would just be sine squared of 20 feet. You all with me on that, class? How many understand that? So if you're given an E field, given an H field, whatever, you can get the power density and you normalize it, then you have this, and then you have to do the integration to get the maximum power density. Y'all with, or the maximum directivity. Agree, class? Y'all see it back there? I'm doing this for a reason. Because the questions I get, but Dr. Baginski, you never gave us an E field, expected us to get the normalized power density. No, but I've asked for the power density, and the normalized is the next logical step. I've showed you how to do it, okay? Everybody got that? Now, what's your question? I'm sorry.
It was a magnetic field strength.
Hold on, let me erase this. So it's a magnetic field strength is given?
Yes.
All right, I'm all ears. Is this from a short dipole, a little Hertzian dipole?
This one, yes, a short dipole of length, lambda over 25.
Okay.
But the magnetic field is 5 microamps per meter.
All right, here's what we got. Got an antenna, right? Got a current I, we know the length, L. Then we're out here at some range, theta, at some distance, R. And here's our magnetic field, H, phi. And what is H phi again?
5 microamps per meter.
So they give you the intensity of the magnetic field, and they want the current, is that right?
The power.
All right, we'll get the power, but we need the current to get the power. So she says the length of this is lambda over 25, right? That's short, correct?
Yes, and then the angle is 90 degrees and R is 2 kilometers.
90 degrees, this is really easy. And R is what?
2 kilometers.
2 kilometers. All right. Class, this isn't drawn right. This should be straight down, but the angle is 90 degrees. You all with me? So here's what we do. We're given the H field, right? So now the logical question is, well, what formula applies to the H field? Well, it's the E field divided by eta. Somebody's going to say, do we need to know the E field equation for a short dipole? Not this quiz, but you will for the test and for other quizzes, all right? Because you'll be immersed in it. So in general, the E field for a short dipole is given as, I like to do this way, J eta beta I L over 4 pi r. You don't have to write this down. There's going to be an e to the minus j beta r here, and then there's the sine of theta. It's in the a theta direction. You don't need to write this down, just here. You all agree with that? That's understood. I know H is just that E field in the theta direction divided by eta, and it's in the a phi direction. That means I get rid of that, so that's j beta IL over 4 pi r e to the minus j beta r sine of theta a theta. Now I've got the equation, the general equation for the H field at any range in the far field. Here's where the fun begins, and it's not hard to see. I'm looking for a magnitude of the H field, right? Magnitude gets rid of this and gets rid of this, doesn't it? You agree, class? We forget about the direction of that. The next is, I got rid of e to the minus j beta r because that's a phase. It's like an angle of 30 degrees, correct? Now what do I do? Well, the angle is 90, right? What's the sine of 90 degrees? 1, so I get rid of that. Now I got all this is equal to 5 microamps, so really per meter, or 5 times 10 to the minus 6, right? You agree, class? I'm not going to hurry here. I want to make sure you see. Do you all understand what I'm doing? I'm equating things down to their basic steps. Now, here's where you watch. Don't react, just watch and listen. Think about what I'm given. A length as lambda over 25, right? So, my length I'm going to put in right here as lambda over 25. And now a light bulb goes off. Beta is what? 2 pi over lambda. I'm beginning to see hope. That J goes away too, right? Y'all see what I'm up to? Take a good, y'all will realize, I knew beta's got a lambda in it, then I see the length is a lambda, so they cancel, which is a miracle, right? Now I look at this, hey, this is solvable, right? I look at this, I got 2 pi by 4 pi, that's just 2, right? Right? And then I got lambda and lambda, that goes away, that gets rid of that and that. And I can take the 25 downstairs and make it 50, can't I, class? Now you can see what I'm up to. So I have I over 50R, and R is 2 kilometers, is that right? You're asking this, I'm showing you exactly the method I would use to do this. I get the current first. So now I get I equal to 5 times 10 to the minus 6 is here, times 50 times 2,000. Now it doesn't matter how you slice this is essentially the same thing. Do y'all agree with that? When you do it, what do you get? Well, let's see. That's 5 times 10, that's 2 times 1,000. 10 times 1,000 is 10,000, right? And 5 times 2 is 10, so it's going to be 10 to the 5th here, isn't it, class? Times 10 to the 6th is going to be 5 times 10 to the minus 1, or 0.5 amps. Do you agree with me? If I did the math right, you'll follow me? We're solving for I. It doesn't use your calculator. So once I have I want the power, right? Please hear me now. It's short dipole, right? P radiated is what? Is equal to 1/2 magnitude of I squared. That's the peak I, by the way. That's not RMS. I squared times R rad. The only thing I don't have is the radiation resistance. I have the I over there, and R rad for short dipole is equal to 80 pi squared L over lambda squared, and in our case, it's going to be 80 pi squared, and this is 1 over 25 squared. And I don't know what that is, but that's the radiation resistance. Y'all follow me? Now, once you have this radiation resistance, you plug it in here to get the power. Did anybody do this problem besides you did it? The answers work out on these. They're right. Did you get the right answer or not?
At first I was getting the wrong answer, but I wasn't doing pi squared, I was just doing pi. So that was
Right here?
Mm-hmm.
Yeah.
So now I got the right.
I'll tell you a lot. You have to have a lot of attention to detail in this stuff. Just level with you. There's little, and by the way, as you get older and your eyes get worse, it really helps me to circle minus signs and blow things up, because I can easily mistake a square that's small for just a scratch or something. Just telling you, if your eyesight's going down the tubes, then blow things up and be careful. And circle minuses. I've learned that lesson the hard way. Okay, any other questions related to the homework? That's a good question. And by the way, all those problems were selected specifically to acquaint you with the different facets of this stuff. Power, EH, you know, the effects of range, gains, everything, okay? We good? Last thing I'm going to touch on right now, not related to the quiz. We've done short dipoles, and I've showed you that the small loops have the same maximum directivity, and that the fields themselves, they have a radiation resistance that's rather complicated. I think he has 320 pi to the 4th, and he's got an S, what is he?
Over lambda squared.
Yeah, and by the way, that formula is not common. That is one that Wentworth came, I don't know where he got it, but at least I'm not seeing it in my EMC work or my radar work, so that's not a common form for that. And usually, I did paste the equations for the H field and E field and stuff like this for loop antennas. Usually, hear me now, When you're in the field, you won't have a single loop, almost ever. What you'll have is a whole bunch of loops that are relatively, the diameter is small, or the diameter is much, much smaller than the wavelength. These are small electrically, and they'll have a whole bunch of loops. And the reason they do is this. Each one of those loops is like adding an antenna in series, and it increases the radiation resistance. Now hear me. Ideally, as an antenna person, I'm speaking from experience, what you want is a lot of resistance, a lot of radiation resistance, so you don't need much current, because current always has losses. The more current you have, the more losses due to heating, all right, ohmic losses. And that's why, and I mentioned this to you, then about power lines having very high voltage, lower currents with the same power. Yeah, ideally, people would like to have power lines with 30 million volts with respect to ground and very little current. Problem is, you hit this point where all of a sudden that voltage is so high that it'll cause corona discharge around the actual high voltage lines, and then you get huge losses. Do you know what corona is? I'm trying to think, is there a good example of corona you can think of? I always think of, the Van de Graaff generators, but that's not corona, that's arc breakdown. It's just like a glow discharge around a charged body. And I can't think of a good one. When the aurora borealis and stuff like this is not truly a glow discharge. It's a glow discharge, but it's not corona. Corona has to do with current. I mean, it's literally causing ionization in very near the actual cylindrical or point, and then it'll cause really light emission. It'll be a high conductivity region, and current will flow there, but it causes a lot of loss. That's my real point. Now, back to antenna theory. Wanted to say that before you get your quiz, and you're about to get it. We've done the short loops, small loops. We've done short dipoles. We explored directivity and stuff like this, but I haven't done patterns, and I haven't had you plot the normalized power density or the directivity versus angle. That's something that's coming up, and it's easy to do. The next thing we're going to do is move into antennas that are long, but straight wire antennas, and get the electromagnetic field from them. But we do that by saying, well, I know the electric field from a short little antenna, so I'll just take the cumulative effects by an integration and get the E field at an H field at a distance by integrating the effects of the current, a known current, over the entire antenna. That comes next time. All right, now, and I know what you're here for, and I ain't to listen to me right here, it's for that quiz. So would you do me a favor, fill in the first row over here after I get rid of it. I tell you what, matter of fact, let's go this way. Fill in that row, and you can spread some desks up that way. Then empty, and that row, and empty, and this row.